And get out my, if you have it, great. If you don't, not the end of the world. But I'm going to grab my star map, because actually that can kind of help with this section. If I have mine. Oh yeah, I have homework to hand back. Do you guys have homework to hand in? I have 2 homework to hand back. So this is what I was talking about. So we're going to be talking about stars, and each one of these dots is a star. Go figure. Do we have homework, Amy? Okay. Thank you. Oh, not too bad.
Yeah.
Very good. What's
Was that the only one we had?
Probably. I wasn't giving him a time. I don't know.
Well, I can remember if you assigned 2 or I was thinking of last one. I guess I got
Homework,
assigned.
maybe?
paper.
Oh, okay, how nice. Okay. Very good. All right. So stars. Gotta love them. Gotta love them. This is, remember, kind of left from right. This is how our star formed, and other stars kind of form the same way. So oftentimes stars are formed in what we call giant molecular clouds. So they're all formed at one time. So you end up with these clusters of stars. And there's 2 types of clusters of stars. There are open clusters, and then there are globular clusters. I kind of dim the lights a little bit so these pop out. Got some more pretty pictures of stars coming up. And then up here, remember we said that, or I said, and I don't need to emphasize it much in this class, but most stars actually have a companion, a buddy. But this is a good example. Like, look at these stars. They're different colors and kind of different sizes, so we kind of need to talk about that. Those would be a pair of companion stars. So this is moving on to the next slide. Beautiful, beautiful. Now these stars, obviously they have different colors, different intensities, okay? They shine with different colors is the first word. The next word is intensities. They have different intensities, kind of different brightnesses. Now, the brightnesses as we see them could be because they're close, they're making it extra bright, or they're just pumping out the energy extra bright. The next one is chemistry. I'll kind of touch a little bit on kind of what sort of reactions might be going on to make this assortment of colors and sizes of stars. The next word, the 4th word down, is quickly. All these stars, stars are kind of grouped, and they have different paths of their lives, different kind of evolutions. Stellar evolution is how a star lives its life. So the next word is end. I think we talked just briefly about Tycho Brahe, where he actually saw a star blow up, or he saw a star blow up. Not all stars blow up. Our sun will not blow up, I think I'm going to say, but it depends on how much mass they have. So mass, speaking of, the word is less there, the less massive stars. So, and it kind of makes sense if a bunch of stars are all born about the same time in a giant cloud, we call it a giant molecular cloud. Some stars get a lot of stuff to make them, and some stars get not much stuff to make them. So we have the massive star and the low mass stars. The low mass stars, they're like the Energizer Bunny. They live a long time. So one of the things we're probably not going to get to is kind of the beginning of our, not our solar system, but the beginning of our universe. And we've actually got stars that were born at the time of the Big Bang, the beginning of our universe, and they've been clicking along ever since. We're talking like trillions of years. And our Big Bang happened some maybe, 15 billion years ago. So a trillion-year star, the last 20 years, it started then, and it just, and then we've also got like high mass stars that died very quickly. It's kind of backwards. Low mass live a long time, high mass live, high mass is right, more massive stars. They have short lives, and they end their lives in explosions, like Tycho Brahe saw. Okay. So just a pretty field of view of stars. So this is where, if you have it, it's going to kind of coincide a little bit with this. And I think I did this the other day. If you look down here where it says star magnitude, so the word magnitude means how bright it is. Okay, so the brightness scale that was started way back in the BCs, actually keep that brightness scale. Here along the bottom, it says star magnitudes -1, 0, 1, which means +1, 2, +2, 3, +3, 4, +4. One of the things that feels backwards is the more negative the number, the bigger the dot, the brighter the star. That's the way it was, and that's the way it is. Each step, though, in the magnitude, and this is what we call apparent magnitude, is a factor of 10. So it's not like a small thing, it's a big thing. Smaller, more negative the number means it's a brighter star. So I don't know if you guys have these on your slides. Anybody do. But just to kind of emphasize, so the more negative, the brighter. So the sun is really bright to us, -26.7. But I'm here to tell you that if you were, okay, here's our sun and our solar system. If you were on a planet orbiting another star and you were to look back at our sun's more like probably, let's see, what is it, like a +4? The moon, really bright, -12.6. Venus at its brightest, -4.4. Sirius, -1.44. Now Sirius, actually, we finally get to, this is a star. It's the dog star in Canis Major, like the big dog of Orion. The naked eye limit, and actually this 6 you might kind of connect up with this 6. With no binoculars, no telescope, nice dark skies, your eyes nice and relaxed, you're looking at no moon, you're looking at about a +6, is about as dim as you can see. Well, you add binoculars, you can push it to +10. We could not see Pluto with binoculars though, and here's why, because a Pluto is a +15.1. The Hubble Space Telescope can get as dim as 30, +30. So here's one for you. In science, we're good about how bright something appears, and we use that apparent magnitude scale. And so our sky map is all about how bright stars appear. But we need to, it's a type of normalization. Sorry. I bet you guys buy this. The word is source up there at the end of that first line. The farther you get from the source, the dimmer it's going to appear. Okay? So, it's hard to know if a star is dim because of because it's not pumping out much energy, or if it's apparently low because it's just far away. Okay, so we have those two things that would make something appear kind of dim in the sky. So what we do, and here's kind of this, what this is showing you is how, like if you step farther away from the light source, this green is the bottom of a candle. Here we have a candle glowing. If you step farther away, what happens is the light has to, will expand and cover more of a region, so light will get dimmer and dimmer. So what we do is come up with, the word here is absolute, what we do is come up with another brightness scale called absolute magnitude. Now this is one of the things that I'm like, really? You did it that way? So absolute magnitude, the variable is an uppercase M, a big M. Apparent magnitude is a lowercase m. The difference between them is absolute magnitude does this sort of normalization process where it takes all stars, and this is a weird thing, but it takes all stars and it puts them at a certain distance from us. It says, well, how bright would they be then? Okay. That distance is 10 parsecs from us. It kind of puts everybody on an even playing scale. So this is what I was trying to say a little bit ago. Even though our sun is very bright, -26.7 magnitude, it's very bright, it's because the sun is so gosh darn close. If we were to go on a planet that's orbiting a star that's 10 parsecs from the sun, notice that then it would actually only be a plus 4.9. We could still see it naked eye, right? Because plus 6 is our limit. But so that idea of kind of making putting all stars on, it's like a starting line, the same distance from us, then actually we can say, well, if their absolute magnitude is thus, then we know something about the energy it's putting out because we've removed the effective distance. Okay? So absolute magnitude of capital M is what we use when we like to compare to a pair of stars or a set of stars. Absolute magnitude. Apparent magnitude, it's got the effective distance. Absolute magnitude, no effective distance. There's two brightness scales. All right. So actually, this says recall, and actually it's in the physics unit that we talk about these, what I call kind of cousins of energies. You can see in this figure, we've got visible light, that's an energy. These are all called forms of radiation or electromagnetic radiation. So notice that another cousin of light or another form of radiation, we have infrared radiation, microwaves radiation, radio waves, okay? Then actually on the other side of visible light, we have ultraviolet, X-rays, and gamma rays. But one of the things I want to kind of focus on for astronomy is that when we see stars that have different colors, that's telling us something about its temperature. Star color tells us something about its surface temperature. So according to this dude Wien, W-I-E-N, he actually said, and he's right, that that objects that are glowing, they are going to glow. Let me grab my. So here we have red. Red is low energy, and actually it's going to be low temperatures. I'll put a T for temperature. Over here, our blue stars, our blue is high energy. The color blue is high energy. And I don't know if you wear it means high energy, like if you're figuring out what clothes to wear. But the color blue also means high temperatures. That was basically what Wien said. Oh, I actually had it here. Duh. So yeah, highest energy, hottest stars for blue, lowest energy, coolest stars for red. So that's one practical thing you can take away. So these are actually, we haven't done a lot of graphs in this class, but the way you look at this data down here is it has plotted along the x-axis here, this horizontal line. It has wavelength, okay? And actually wavelength is color. You can kind of see the colors. When we talk about colors being different wavelengths and colors being a certain order, sometimes I tell people Roy, R-O-Y, red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. That's from the longest wavelength to the shortest wavelength. But my point here is that what's been done for this plot is we have a wavelength here, okay, and then we have how intense it is here along the y-axis. And then here, actually kind of just tick marks. We've identified, or somebody's identified on this figure, what that object is. So in other words, a human person, which runs, K means a unit of temperature, Kelvin. So a human temperature who runs a human person who runs about 310 Kelvin will have this sort of distribution as it glows. Notice that we're not glowing actually any visible light, we're reflecting visible light, but what we're glowing actually is going to be here in the infrared region. Now, stars here, let's go back up and go up to this red line. We have 3 stars of different temperatures. We have a star, the temperature 3000 Kelvin, the sun, a temperature of 5800 Kelvin, and another star that's a whopping 1500 Kelvin. What they've done actually is to go ahead and with the color of their line show you the color that we would see them as. we would see this cooler star as red, we would see the sun as yellow, we would see this hotter star actually as blue. And kind of showing you how this works, can you see where the red one actually peaks over here at the longer wavelength? The blue one peaks here at the shorter wavelength, most energetic. And that's all kind of what's going on behind the scenes to make those stars different temperatures. That's Wien's law. So the word is blue and red. So the blue stars are hotter, the red stars are cooler. Bottom line. So one other thing about, and this is one thing we'll talk a little bit about in the chemistry unit. I said these are all standalone units, but I guess they aren't entirely. One of the things, and I'll kind of just put this in context aside from the chemistry part of it, but what you're looking at here, the A, B, A, F, G, K, M, these are all different types of stars, and it's not like DNA, but it's kind of like DNA. These lines we call spectral lines, and these actually identify the type of star. Underneath, for instance, the G type of star, we can see the element oxygen. Underneath the A type of star, we can see the element iron and calcium are kind of making that pattern. Underneath the B type of star, we see helium and carbon are making those spectral lines. So the word is absorption and emission. These up here, these what I call just now spectral lines, are actually what we call absorption lines. They're nice and dark. They're absorbing the energy at that particular light, at that particular wavelength of light. Bottom line is that astronomers can study these patterns of light coming from a star and understand a lot about that star. You see this O, B, A, F, G, K, M. Right off the bat, they can get the spectral information from a star and go ahead and match it up to what this, there's 7 types here, what spectral type it is. The word is elements there. They can know what elements are present on the star. How awesome is that? Pretty darn awesome. The word is temperatures for the last one there. Notice with these 7 spectral types, along here, along the, let's see, left and right, the left side of them, the K means the temperature of Kelvin units. So notice that we have 30,000 Kelvin, 20,000 Kelvin, 10,000 Kelvin, 7,000 Kelvin. Well, that's getting, I guess our sun is about 5,800 Kelvin. So our sun is actually a G-type star. 6,000 Kelvin. But they're getting hottest to coolest. So this 7 spectral types indicated by the capital letter over here, O, B, A, F, G, K, M, are ordered by hottest to coolest, okay? And there's a mnemonic device for everything, including the order of hottest to coolest star types. And it goes O, B, a fine, either guy or girl, kiss me. So O, B, A, F, G, K, M. All right. So scientists, including astronomers, love to make plots. And actually, these 2 individuals by the last name of Hirschsprung and Russell, independently were looking at star data and trying to kind of see what they would look like on a plot. So they made these, the word is patterns. They made these scatter plots, a scatter plot that is known as the Hirschsprung-Russell or HR diagram for stars. So let's see what they decided to kind of plot. Well, they plotted surface temperatures of the stars. I just think that is so cool, no pun intended, that we know what the surface temperature of a star is. Notice actually we go from hottest to coolest, which feels a little backwards along the x-axis. We have a double x-axis. If you look up there for x-axis, you see the hottest is O, then we have the B, then we have the A. So O, be a fine guy, kiss me, going across the top there. That corresponds to the hottest to the coolest temperatures. Now, along the y-axis, we have two, kind of a dual scale too. Luminosity, and I don't know if I've really talked about luminosity yet, but luminosity is the energy that the star is pumping out. Notice that luminosity, though, goes hand in hand with absolute magnitude, how bright it appears if it was 10 parsecs from us. So absolute magnitude goes hand in hand with how much energy it's pumping out. So with all of that in mind, okay, when they did that, what we do with scatter plots in science is we look for groups, we look for groupings. And I don't know if you see them, I'll go ahead and circle them on here. I actually saw some groups that end up matching up with the behavior of a star. So each one of these circles are a star, and actually this figure actually went ahead and named the stars. Isn't that nice? Right off the bat, you see main sequence. So these are our main sequence stars. They're kind of a diagonal from kind of upper left to lower right. And that main sequence actually is a stage of a star's life. It's the first stage of a star's life. After main sequence, it kind of depends on how massive a star is. The way this works is, I'm going to go ahead and put most massive up here and least massive down here. Remember those red stars I said that have been around ever since the beginning of our universe? There they are. Okay, so we have the most massive stars up here. Most massive. I'll just put, massive. I'll just put mass. And then we have the least massive here. Mass. All right, giants. Let's see. Giants are kind of over here. I kind of take giants and supergiants and say that they're both over here. So giants over here. Supergiants kind of over here-ish. I don't know if I mentioned in this class, I kind of get my classes mixed up, but Betelgeuse is one of the awesome red stars in the constellation Orion. White dwarfs. White dwarfs are down here. So based on kind of what I've described, can you see where these guys over here, these guys on the main sequence, they are very luminous and very hot. Well, let's look at the white dwarfs. Let's see, they are very hot because they're over here, but they're not very luminous. They're not pumping out the energy. I will go ahead and tell you that the white dwarf is how the sun is going to end its life. So here's the sun. The sun is going to, after it's on the main sequence right now, as it evolves into its next stage in about 5 billion years from now, it's going to move on the HR diagram up here. What does that mean? Well, it means it's cooler and it's luminous. The reason it's very luminous is because it's swollen. That's the scary part of our sun becoming a giant. Then it's going to actually, after it kind of ends, runs out of hydrogen, runs out of helium maybe, it's going to end up right here. So our sun is right here now, it's going to become a giant, and then I don't know how long from there, but it's going to end up here. So things move on the HR diagram depending upon kind of how it's living its life. The word is blue there. So for the main sequence stage, the blue stars are most massive and the red stars are least massive. The blue stars are hottest, the red stars are coolest. Most people can buy into this. The problem with the massive star is it's so darn hot that actually it churns out, it runs through its mass quickly, and so that's why they have short lives. These guys down here don't have much mass, but they're not pumping out a bunch of energy per second, so they can live a lot longer. Right. So when we talked about our sun, we said that in the core of our sun, that's where we have nuclear fusion going on. Does this maybe look like nuclear fusion to you? We have hydrogen plus hydrogen plus hydrogen going to form helium. I know I said just 2 hydrogens, but it's more complicated than that. This is more accurate. In our sun, we have hydrogen fusion going on to form helium. And that's what all those main sequence stars are doing. So the first stage of any star is going to be the main sequence. And again, the more massive it is, the faster it's going to live its life on the main sequence. The less massive, it's going to live there a long time. The word is faster. The more massive the star, the faster they burn through their hydrogen. So what do I mean by massive? So it could look something kind of like this. Where if we talk relative to the mass of our sun, well, I guess it's coming up. So, for instance, I have 10 solar masses, 10 times the mass of our sun and another star. I have another star here that is the same mass as our sun. And then I have a star here who's half the mass of our sun. So with regard to how long they live, I told you the massive ones live a short amount of time. You're only talking 20 million years. Now get your M's and your B's. Don't get them unconfused. Because our sun has been doing what it's doing for about almost 5 billion with the B years. So can you see where if it was more massive, it would have left the main sequence, and depending, it may have well, this one's actually going to blow up. I think 8 is the threshold for blowing up. So it would have blown up. The star with our mass, like I've been saying, we're about halfway through being a main sequence star. We've done 5 billion. We have about another 5 billion to go. That's where the 10 billion comes from. And again, if you're a low mass star, you're looking at 80 to 100 billion years. Okay? Wow. And our universe has only been, I want to say, 14, 15 billion years. Yep. So the number there is 5 billion years. So it's all about us. But one of the things I find humbling, one of the many things I find humbling about the study of the stars is just how long they last, how long they've been there. And I think the other thing we've touched on is that most stars have planets. So you're like, I think there could be other life out there. All right. So what happens as a star leaves the main sequence? Well, it depends upon the original mass. Okay, it's all about mass. So we're going to try to talk about these different possibilities for a star to end its life. What does it do? I already kind of showed you a little bit how our sun is going to leave the main sequence, become a red giant, and it's going to cool down, probably give us a planetary nebula somewhere in there, and then it's going to become a white dwarf. So on the HR diagram, I'll kind of just quickly do an HR diagram. Remember, you can put a couple things down here. You can do I'll do this one, O, B, fine guy, kiss me. Or this is hot, and this is cool. And then I'll put luminosity, which is the amount of energy the star's pumping out, and I'll go increasing luminosity. And then, so these are the main sequence stars. These are our giants. These are our supergiants. So if you ever have to draw this on a test, hint, hint, something like this would work for you. And then down here we have white dwarfs. But you probably only get credit if you make sure that you label the axis and then mark the groups. My point here, and then up here, these are the most mass, and these are the least massive on the main sequence. These are cute little red stars, sometimes called red dwarfs, just like the TV show. Bottom line is these guys, I'll just make my dots my stars. These are stars down here. These guys, they're not going to become giants, and they're not going to become white dwarfs. Basically, they're going to eventually, in 80 to 100 billion years, run out of energy and turn into a brick. What about other stars? Well, and maybe this is where I'll go ahead, and this is my star mass.
What's it say on the left-hand side there?
What's that?
On your scale? What's that?
This one, luminosity increasing. So my star mass will go, if it's 0.4 times the mass of our sun, this symbol means the mass of our sun, to about, 8 times the mass of our sun. Okay, these guys right here, they are actually going to, these are what we call low mass. They're not really low mass, but they're low mass. Low mass stars. And what they're going to do is they're going to go, our sun is one of them, they're going to move up here. And one of the things I didn't tell you, and I think I have it on a slide coming up, is actually in their giant region, or somewhere up in here, they can form these cool kind of ghosty, this is my ghosty looking thing, called planetary nebula. All a planetary nebula is kind of, it's a giant and it's kind of sloughing off its material and it's kind of cooling, or it's near the end of its life. And then after planetary nebula, it's going to become a white dwarf. Okay, and as a white dwarf. And again, white dwarfs are down here, so that means they're not very luminous because they're down here, but they're pretty warm. And they will eventually, white dwarfs eventually cool down to become bricks. A lot of bricks out there. Well, what about the more massive stars? So if we go from 8 to 25 solar masses, what's going to happen to those guys? They would be up here, right? What they're going to do is leave the main sequence. They're going to probably go super giants, maybe kind of wiggle around a little bit. They might form planetary nebulas. But then what they're going to do is they are going to blow up, okay? And as they blow up, they're going to leave something kind of in the middle of their blow up, and that is going to be a neutron star. Okay? Well, there are suns out there, and the threshold's about 150 solar masses. That's just too big. But somewhere between 25 and 150. Wow. These guys are gonna. So these guys are considered high mass. They're both considered high mass. These will give you a neutron star. And these actually, after they'll blow up, and they will give you a black hole. So that's kind of how that goes. So I need to talk a little bit about neutron stars and black holes coming up at the end of this part. So let's see what our sun's going to do, because our sun, you figure our sun is 1 solar mass. Does that make sense? So between 0.4 and 8 solar masses. So our sun is 1. So this is what we're going to do. This line here is the main sequence. You kind of see it going up there into its giant phase. It kind of does some wiggling, it might be a variable star. This is the planetary nebula, the kind of the last little, I think I'll just give my matter back so another star can be born sort of thing. Okay? So planetary nebula, and I have some photos of planetary nebula coming out. They actually picture a little star in the middle that's kind of on its way to becoming a white dwarf. That's a planetary nebula. So a high mass star, high mass would be actually more than 8 solar masses, but we kind of have 2 types of high mass stars. One type of high mass star, they're both going to blow up. One's going to give you a neutron star, one's going to give you a black hole. So what they do is they actually become supergiants. They'll blow up, The blow-up event is called a supernova, and then like I said, what they leave back behind is a little pit that's either going to be a neutron star or a black hole. So this is not a planetary nebula. By the way, planetary nebula, I know it's weird. I'll go back here to my low mass star ending its life. They have nothing to do with planets, planetary nebula. Only what they had to do with planets is they were actually then mistaken for planets before, just because they have that kind of nice little circle to them. This right here is this the same one that Tycho Brahe saw? No, maybe. But this is Messier object number 1. It's called the Crab Nebula, and you can kind of maybe see kind of the nebula just means a gas region. You can kind of see the red gases here. And it's the guts of a star that went supernova. So here's the result of a supernova event. And in the middle of that actually is a neutron star. So these are not my photographs. These are some photographs of some planetary nebula. Remember over here, if I was going to put planetary nebula somewhere, I would put it right here with my low mass stars. They will give us planetary nebula. They have nothing to do with planets. Other than, like I said, they kind of look like planets, maybe. But they don't wander against the background. So there's one. I think that might be called the God's Eye Nebula. In addition to the Helix Nebula. Dumb Nebula, looks like bubblegum. I can kind of see that. Very clever. Butterfly Nebula. And again, they have nice, cool little names describing what their shape are, but these are all examples of planetary nebula. So again, we should be able to find a central object, a central star, that is actually on its way to becoming a white dwarf. So these would be all low mass, and our star is going to give somebody else a planetary nebula. Glowing pool nebula. So let's just kind of talk briefly about if a star does blow up, a massive star, more than 8 solar masses, high mass star blows up. What is the nature of those two objects that we might end up with? So a neutron star. Well, you've probably heard of neutrons before. When we get to our chemistry unit, okay, if I'm drawing a picture of an atom, I'm going to draw a neutron and I'm going to draw a proton. So I'll just go ahead and draw a couple of them. So these are my neutrons. And these pluses are my protons. And guess what? This negative is my electron. So for a normal atom, we have this kind of in the center we call the nucleus. And since I have 2 protons, I'll throw 2 electrons out here, kind of outside the nucleus. So the awesome thing that happens during the explosion of a massive star that's going to create a neutron star is basically the matter squishes down to kind of turn protons and electrons into neutrons. So you end up with neutron soup. Oh, the word is supernova up there. So a star between 8 and 25 solar masses is going to explode. It's got to. It's kind of the physics of it. That explosion is called a supernova. And it will leave intact a neutron star. I mentioned compact just a minute ago. So how compact do we mean compact? Well, if you were to visit a neutron star and bring back a teaspoonful, it would weigh 12 tons. One of the things about cute little atoms up there, like I drew, is they're mostly empty space because the electrons have a lot of volume. The nucleus, the center of an atom, not much. And so they're really kind of fluffy. So I kind of mentioned the consequence of having such squished material together is, like I said, it makes the electrons and protons of normal atoms change into neutrons. Really? Really. That's what pressure will do to you. So you get the neutron star. So picture this blue thing is the neutron star. This is the thing that was left over after the star blew up. Neutron stars, you're like, oh, they're dead. Well, actually, we can see neutron stars. How can you see neutron stars? If you ever hear anybody talking about a pulsar, I don't know where it is. If the word is pulsar, anybody talking about a pulsar, they're talking about a neutron star out there. And this figure tries to kind of show you, how do you see a neutron star? Well, it's such a crazy object that it actually has these, you kind of see these, kind of these shaft of energies, one going up, one going down. It's like, well, how can you see that? Well, the other thing is this white stick right here is it's rotating on that stick. So the thing is if you happen to be, if you guys are Earth, okay, and I'm a shaft of energy coming from that neutron star, it goes blip, blip, blip. Okay, so you get the energy blip from a neutron star, okay? And so the blip, blip, blip is pulsar. Actually, they used to not know what they were. They originally, and you gotta just love scientists, they were usually, they originally called LGM sources, little green men, when they were first found. Because they're like, who's pulsing us? Wow, civilization. Like, no, it's just a rotating neutron star. The last thing I just want to quickly point out is what's up with this black hole. What is the nature of a black hole? And I'll warn you up front that this is not the only way we get a black hole. This is what we call a stellar black hole. And again, it would be a star as if it was on the main sequence that's more massive than 25 solar masses. Okay, so how do you get a black hole? The word is collapsed. So I mentioned neutron stars are very dense. Black holes are so dense that basically they have created a hole in the fabric of space. They have created a hole in the fabric of space. So here we go. Black holes have this in common, whether they're black holes that come from a star that blows up, we call those stellar black holes, or whether they're the black holes in the center of the Milky Way galaxy, because that's so what it has. Okay? There is a point associated with a black hole called singularity. And then there is a region outside singularity associated with black hole called the event horizon. And here's the deal. The event horizon, which is outside the point of singularity, any black hole, whether it's a stellar black hole or a supermassive black hole in the center of the Milky Way galaxy, that event horizon is a do not cross this or you're screwed sort of thing. So if you're inside the event horizon, you cannot escape, even if you're going the speed of light. If you're outside the event horizon, you have a fighting chance. So we can see neutrons. We can see the presence of neutrons with pulsars. Neutron stars with pulsars. And actually, we can see the presence of a stellar black hole if it has a companion. And actually, most stars have companions. Here's how that would work. So here is our alive star, and actually some of its material is being siphoned off to its companion. Its companion actually is a black hole. So this material will go faster and faster and faster and basically become part of the black hole. And as it goes faster and faster and faster, you can kind of see these squiggles. It's a kind of I think, a friction thing. It creates energy that creates a signature. In this case, X-rays, that we know that there's a black hole there. All right. So these will be due tomorrow when you can take your test. Or you can make it Friday.
Oh, I didn't see that.
Yeah. If you wrap it, like I said, you can do it Friday, but I just want you guys to be ready for your test and do good on your test. And so there won't be any part 6 questions on your test. I'm ready for normal weather. It's hard to teach with all these missing days. So be careful out there. And if you end up not coming because the roads you just can't get here, give me a quick message and see what we can do.